can I go first? Tomo-san? I can't hear you, but can I go first?
Yes.
Okay.
Connect with your account, not my account.
Oh, I'm not muted.
Okay, so can I start?
Yes.
Okay.
Can you hear me? There's nothing there.
Okay.
Can you hear me, Yuri-san?
Yes, I can.
Oh, okay. So please go ahead.
Thank you. So today I'd like to summarize the posters about the birthday. Tomo-san, our group recently collaborating. And okay, anyway, so Vertex is a project to launch a satellite to understand the extragalactic background light called EVL. And previous observation of the near infrared that so we found the excess of the near infrared light from the integrated galaxy light. This means if we know the integrated light from the known galaxies, the brightness should be this gray line, but the actual observation is much brighter than the integrated galaxy light of known galaxies. And so this excess is, we still don't know why this excess happens. And there are two main hypotheses this excess might come from. One is intrahalo light, which is our, if we assume that galaxy's halo has more brighter than it was assumed, maybe this excess of light come from this halo from these galaxies. And another hypothesis of this reason of the excess is maybe this light comes from the first stellar object. That means the stars, when the stars in our universe. Something like this. This is the schematic figure. So yeah. So extra EVL is all the light comes from the early universe. So that's right. Okay. Anyway, so let's go to the satellite system. So in order to understand the origin of the EVL, they need a high spec satellites, such as high-speed data transmission and good pointing stability and wide field optics. Then here is the detail of the how spec of the satellites. And maybe I don't need to go to the detail, but here explain what kind of spec needed to the satellite. And okay, so here I explain the detail of the satellite, and they have the 3U bus system and 3U mission payload. And 3U means this U is a unit of the satellite research field, which is not I was not familiar with, so I looked it up. And 1U is a cube with dimensions 10 centimeter times 10 centimeter and times 10 centimeter. So that means 10 centimeter cube, kind of a cube with 10 centimeter in the one, how can I say? Anyway, then, so bus system means they have the 3U size core and 3U mission.
Is there something else I can help with?
Sorry. And 3U mission payload means that mission payload has 3U capacity or size. Then, yeah, for example, bus system has a, oh, sorry. I think, sorry, me go. Oh, yeah. So bus system has something like power and computing, and the mission payload has the part where mission payload is a part where they have the observation tools like telescopes. And here they explain the current status of the mission. It says the satellite is under development. Then, oh yeah, here explain the detail of the satellite structure, such as here payload and communications. So communication happens X and S band. Then wait. Okay. So S band is used for sending commands to the satellite, and X band is used for receiving the data. Then, yeah, in a bus system, they have, as I said, they have this kind of necessary stuff for the satellite. And this poster also explains the funding resources. This is the first, this Vertex project is the first project that was selected by the JAXA SMASH program. That means this project is supported by the JAXA. And this is the one paper, one poster. And do you have, I also want to show the other posters. So do you have any questions so far?
Sorry, Yuri, I missed the early part. Did you mention the science?
Size?
Did you mention the science?
Science. What is it?
Science.
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 Yes. I'm not sure if I explained very well, but I kind of explained. So this project is to understand the origin of extragalactic background light. So recent observation of the near-infrared, they found the excess in the intensity of near-infrared from the sky. And if we integrate the all light from the non-galaxies, this light intensity of light should be this gray curve. But actually, it's the observed values are more higher than the non-light from the galaxies. Light from the non-galaxies. So we don't know why this excess happens. That's why this project wants to know what it is.
So there are two models, blue line, first stellar object, and also second red line.
Yes.
Intra-halo light. I don't know what it is, but so by
light is,
this,
okay, it's the halo light from the galaxies. Maybe the current model doesn't include enough
Yeah,
halo.
so because they are measuring very dark part of the sky. So maybe some unresolved light from the each individual galaxy might be accumulated. Maybe
Yes.
they mentioned this. And then by this project, so they can basically exclude the second, so the red curve.
Yes.
They expect, so okay, so we don't know whether which one is excluded yet,
Yes.
based on the result. Okay,
Yes.
sensitivity is enough to reach the.
As far as I can see from this figure, seems like optical observation hasn't done much. Then, if we could, because vertical sensitivity is enough to resolve these two curves, like showing a blue highlighted line. Yeah, that is why they are doing this project.
Okay.
It's okay.
Yeah.
Thank you.
Any other questions, comments? Maybe Yu-chan, do you have any one more poster?
Yes. So maybe if I still have time, can I go?
Yes, please. Go
Okay.
ahead.
Let me check. Yeah, so this is another paper how they wanted to select the observation field and how observation happens. And this is so it seems like this four band is separated. Sorry, I didn't say maybe. So this particle satellite has four bands, four optical bands. And this one square shows the each field overview of the each four bands. And so each band has 3 square degree field of view. So in total, they become 6 square field of view, 6 square degree field of view. And so they are going to observe the same region. Oh wait, one region for 4 bands, and this red marker shows that where all 4 bands, where the area that observed by all 4 bands. And
Is your screen frozen?
eh,
See
but
your screen.
you're not seeing the screen.
Yeah.
Now we see.
Now we see.
Okay. Oh, so maybe I can start from the beginning. Okay. So vertex has 4 optical bands, and each band have the 3 square degree field of view. So in total, they have 6 square degree field of view. Then they are going to observe some part of the area with 4 bands. So the image of the observation is like this. Then seems like one area should have the overlap the area of 9 times 9 degree. Then probably this is one set of observation. Then here is a field of observation. They said they want to observe 35% of the sky area per year. And as Shodaro-san mentioned, so we need to extract the because this observation, we are observing all the light from the sky. So we need to extract some components in order to know what is the true luminosity of the EVL. They are going to have multiple observations in terms of the multiple goals. And here are some components that they are going to extract, such as zodiac light. Zodiac light is light comes from the dust, which is interplanetary dust that is scattered by the light is scattered by the sun. And another component that should be subtracted is diffuse galactic light. This is light scattered by interstellar dust within the Milky Way. And also integrated starlight. This is the light from the Milky Way galaxies. And yeah, then finally, by subtracting these components, we can know what is the true luminosity of EBL. Okay. Then they already run the simulation, what kind of observation will going to happen, or to check their how can I say observation plan. Then so here is the image of the observed simulated observed data, and this figure 4 have the multiple components, as I said, like zodiac light, and DGL, ISL, and EBL. And then from the simulation, they kind of found out, they successfully, they simulated, how can I say, they simulated the they simulated the luminosity of the sky, and also simulated the observation to this simulated sky. Then they said they get the expected result from the simulation and also simulated observation. So they say their plan should be fine. Yeah, that's it.
Okay. Any questions, comments?
I think what they did is just a simulation. So basically putting EBL some specific value and creating a universe with this EBL with some model, foreground models. But I'm not sure how. I don't know. Maybe this model is based on the observation from at the larger wavelengths, maybe different wavelengths. But I don't know how. Maybe pipeline works, but we don't know whether this subtraction actually works at lower frequency, at lower wavelengths. I don't know. So I'm not sure if this really, at least this pipeline works, but we don't know how much uncertainty and how much model dependence affect the result. Because I think zodiacal light has huge uncertainty, and also diffuse galactic component is also a huge uncertainty. These two components are the major foreground noise. So I don't know, because I often hear people always discuss the huge uncertainty in these models. Actually, this actually prevents us from telling exact EBL. So, but it looks nice. So it's kind of comment, but I don't know the detail, of course. So what's the kind of period of observation? How long do they observe? And at what time scale do they get data set?
Well, let me check.
Maybe previous poster?
This one. Does it say anything about observation plan? I'm not sure if I found it.
So to answer Shotasan's first question, yes, as Shotasan said, these foreground lights are much brighter than the background light. So accurately subtracting these foreground light is very important. So that's why. But then this zodiacal light, for example, is a very large scale. So, Yuri-san, could you go to the second poster? So it's very important to model it accurately. It's very important to observe the very wide field. If you notice this blue one, ZL target, it's much more field than the actual target is orange, right? But then the blue one, foreground, is much more area, right? That's because they want to model it more accurately. And then this satellite has a very large field of view, so at least they can model the foreground light more accurately than other telescopes. And the observing frequency, I forgot. I thought a few minutes exposure one time or something like that, and then just they go bam, bam, bam.
I see, Tomo-san. Nice. So I also noticed their kind of coverage of the sky is following the zodiacal light distribution. So it's okay. Then EBL target depends on the maybe they try to select the higher latitude, relatively dark region, far from the infrared bright cloud. So
That's
I think, okay. So basically the strategy is the same as previous survey, but they do this at different wavelengths with huge coverage of the sky with nice modeling. Okay, looks nice. Okay.
Just to answer beginner's comment, dark cloud method is a separate method. They are also going to try, but it's separate from here. So, or maybe you can review a poster or paper about that.
Tomo-san, actually I did dark cloud, this method when I was undergrad.
Oh, maybe then Shotaro-san, maybe could you introduce the method?
Yeah, it's simple, just a subtraction.
Yes.
So yes, of course. Maybe I can, or maybe Vignesh can.
I think there's a poster about that method too.
Okay.
Okay, then shall we move on? Thank you, Yuri-san, for or two posters. And then shall we go to Jim? Yeah. Okay, please use the microphone. Are you going to read two papers?
No. Just one. Okay, I think you can see screen. So I also already post this in Facebook, and this is another, I think, very interesting paper on little red dot. So the conclusion is already written in the title, but the main point that this paper have done is that then they compare the number density of little red dot and the very luminous quasar, and they conclude that little red dot couldn't be the quasar counterpart for lower luminosities. So I skip this very long introduction. First they compare this luminosity function of the little red dot and the quasar, because if we consider the luminosity of the little red dot, there's only you only have quasar have the similar luminous with length, so it's the only comparable things if you want to study them. So some may think very straightforward, thinking that quasar. A little red dot is maybe a kind of quasar, but if we compare the luminosity function from the quasar list solid line and the luminosity function from those little red dot paper, you can very clearly see there's a very large discrepancy from 40 times to 2000 times. So
which one is which?
So the dashed line is little red dot, and this solid line is quasar at Q ratio. And also, we can see little red dot don't have a obvious evolution from this ratio 7 to 5. They seem to be non-evolution. But okay, so from this, they propose two assumptions. One is that here. Okay, there may be a large part of obscure Adrian or quasar population in this lower luminosity range that recently found in JWST, and maybe the large part of obscure Adrian population can extend to higher luminosity range compared to the bright quasars. So the things they want to discuss is that LRD is kind of as the same type of quasar with the similar evolution mode or not. So they do a very complicated analysis here, which they calculate the Hero mass function for. They have their own method to calculate the Hero mass function for quasar, and from this quasar is just a UV luminous object, and so they compute these two according to different luminosity. They have these two red Hero mass function, and if you consider the number density of LRD, which means that if you assume all these LRD has the same host halo as the quasars, then you can multiply this curve with those number density, and you will get this purple line. But if you compare this purple line to this total Hero mass function just derived by lambda CDN, you can see this. They are already evaluate this dash. This I think is the upper limit from theoretical. So if you need to keep this such high number density for LRD, then the Hero mass distribution should not follow the shape for quasars, which means they should be located in a smaller halo, less massive, not like this. And they also did kind of mock analysis to showing that with this parameter setting, they can apply for some observation that with ZWST they can separate different dirty cycle between evolution, different evolution scenario. But this part I don't really understand it. I think this is too details to say, but this mock analysis is the point is just saying that we have approach to distinguish the evolution mode of LRDs from ZWT. I think this is serving to their proposal or something. But as like I said at the first, the main point is that they show LRD should be a different population from the UV quasars that is only known sources before the diversity at this redshift and luminosity. And if you look at this luminosity density history, you can see LRD have a very large contribute to this luminosity density. Yes. Although they are saying that uncertainty may be very large, but should be a new population. Yes, I think that's from the paper.
Okay. Thank you very much. Any questions, comments?
Jimmy, I have a question.
Okay, maybe some questions and then process.
Sorry. Mine is quick. So I think you are saying this expected number of halo is exceeding upper limit. If you assume maybe 100% of little red dot is this quasar counterpart, then this is going to over upper limit, right?
Yes.
So then, but actually part of little red dot may be quasars, right? So do they give some upper limit on this fraction? Or we can read this from here?
I don't think they have.
Oh.
Compare the luminosity function.
They assume these fractions, which way?
The number density is 40 times difference.
Yes.
So only few percent may be quasar.
Maybe you can read the value in this table. They have some fractions to make their Hale mass function.
How do we read this?
So they just multiply this fraction by UV luminous active fraction and the obscure fraction.
So that means obscure fraction is
So log 1.5.
I misunderstand, sorry. I think they are saying there are more obscure to agents, right? Or quasars, right? If they are quasars. I mean, if they are quasars, there are more obscured quasars than UV luminous ones. So therefore, how many at the most?
It's actually greater than 1, which is uncritical.
Yes, yes.
Sorry.
Okay.
So maximum is limited by gray light. So therefore, maybe middle point between.
Okay.
I'm sorry, I'm not sure how to calculate this.
Maybe we'll go to contact question.
So how do they infer the redshift of little red dots? By only photometric redshift or?
Yes.
So what is the little red dots are actually has lovely solutions that actually overestimate the intrinsic.
That's the systematic in the all of this little red dot research. But
So no one.
I think some of them have the photometry, no, spectral observations. Maybe they write something in paper.
Okay.
Yes, they include both. So some of them must be in that pressure.
In figure 1, you mentioned that little red dot will not have relationship even.
No, I think they just describe these things, but there's not the
They don't have any inference.
inverse from. No.
They might have done a lot of, complicated modeling, but first of all, we do this red dot is just selected as red, right? There's no way all of them are greater. Of course, if you select objects, then there are, most of them are galaxies, no? AGN. AGN is 10% or less usually. So, I think the answer to this question is very obvious from the beginning.
But I think people think real red dots are AGNs because no, this also not decided. It's still under debate.
So most people believe little red dot is greater.
It's AGN, but with that luminosities, the only comparable things is quasar. So that compare that with quasar, but the answer is they are not quasars.
Okay, good. Any more questions? Okay, if not, thank you, Jimmy. And then I want to introduce our paper. Thank you very much. Okay, so I want to introduce this paper at the first very long baseline interferometry detection at 870 micron. So this is obviously from the Event Horizon Telescope collaboration, at least most of them. And then, if you remember, so everybody knows that the black hole image of the Event Horizon Telescope, right? It was a big news, right? Do you remember that? What wavelength or frequency was that image? That's 1.3 millimeters. Okay, so because it's easier to do interferometry in longer wavelengths, 1.3 millimeter is already pushing because it's a millimeter. You know, usually people do that in radio, much longer wavelengths, right? Radio interferometer. Burst telescope is much longer wavelengths, right? So shorter wavelength interferometer is more difficult. But now they're pushing it to 870, from 1.3 millimeter to 870. So about 1.5 times shorter wavelengths. That means the resolution is 1.5 times better, right? The resolution just go d over lambda, right? Lambda over d, right? So the d is the baseline, but the baseline in this case is just the size of the Earth. So either we make the size of the Earth bigger, or make the wavelength shorter, which is easier, right? So they are making it with the shorter wavelengths, and then they succeeded. That's amazing news. So let's look at it. And then, okay, I should mention that not all of the Event Horizon Telescope are participating. So it's not really, oh, you can see the cursor. Then it's not really Event Horizon Telescope, some of them. But you see this one, right? Greenland Telescope. That's Taiwan's telescope. It's also here participating. And then, of course, ALMA, SMA in Hawaii, and then Aram Noema in Spain. So as you can see, the baseline is about the Earth size. Then let's look at it. So they observe a bunch of AGN. So these are AGN, various of them. And then Greenland Telescope is participating here, but then the weather at the Greenland was not good at that time. So in the final results, there's no Greenland Telescope data. It's unfortunate. I should also mention 870, the tau is much higher. So observation is more difficult. You need a even better weather than 1.3 meter, 3 millimeter. Okay. Then, okay, let's go to the result. So this is a fringe, detecting the fringe with time delay, so that's good. And then maybe I should mention here. So this is the UV plane, and then as you can see, those colored ones are detections at several baselines. So this is ALMA Apex, ALMA SMA, ALMA Alam. This is ALMA SMA, and different symbols shows the different agent they observed. And they detected, and then you can see, so this is UV plane. So the larger the circle, the better. So this circuit's resolution is in this gray, 50 microarcsecond. This is 25 microarcseconds. And then these gray ones are previous Event Horizon Telescope UV data. So previous resolution was, I forgot, something like 25 micron. Previous resolution was 25 micron, or maybe a little bit better. But now detection is here, right? And if you look at this circle, is 90 microarcsecond here. And then this is the highest resolution interferometric observation on Earth. And then that they achieved in this detection. That I think this is amazing. Then they did the simulation. So this is simulation. So here, let's look at it. So here, so this is black hole image. This is Sagittarius A. And 1.3 millimeter, the simulated image look like this. This we already observed on the newspaper. We saw that on the newspaper, right? But now, if we move to 0.87 millimeter, 870 micron, then the resolution is 1.5 times better, right? So we're going to get even sharper images. So theoretically, they can go to the Earth side, something like 15 microarcseconds or something like that. So that's even better. So this is just reporting. So these are simulation, right? But then they are doing a simulation to observe later, right? So probably, I don't know, in the near future, maybe we see image like this when they do the observing campaign. So, stay tuned. Maybe they'll put another Nature paper. Okay, any questions, comments?
Tomo-san, in this simulation, they include the Greenland telescope?
That's a good question. I didn't pay attention.
But maybe simulation, maybe yes.
Must be, because there are a lot of baselines here.
Okay.
A lot of baselines, so I think so. I didn't check it. Figure 9. Yeah, so theoretically, they can go to 50 microarcseconds. This time, 90 microarcseconds. Yeah, I think they say simulation is for event horizon telescope, so I think they included Green Island and everything.
Okay, thank you, Tomo-san.
Any other
Tomo-san,
questions?
sorry.
Yes.
Do they actually observe those AGN, or is this totally simulation paper?
No, they observe. They observe them actually.
They did.
Yeah.
They did, right? Okay.
Yeah.
Okay. Oh, nice.
So these are detections.
Okay. So maybe the modeling is might be separated from
Modeling is for the black hole shadow. So these are like point sources, right? These are more distant black holes, so just detection only.
I see. Okay. Thank you.
Okay, if there's no more question, then it's time to stop. So who wants to volunteer tomorrow? Oh, good. Okay. Sitting under me. Okay. Thank you very much. Salmon. Okay. Salmon and then sitting. We need one more person. Oh, okay. Sean. Thank you, Sean. And then Simon too. Oh, is there anyone else? Okay, so tomorrow we have Salman, Sitin, and then Sean. Okay. Thank you very much for speakers today, Jimmy and Yuri-san. See you tomorrow.
Thank you.
Okay, thank you. Bye-bye.